So our speaker today is Jasper Wassenburg. Jasper completed his initial degrees in geology from the Netherlands, and then followed by his PhD and postdoc positions in Germany and the UK. And he's now a young scientist fellow and research professor at Busan National University. I'm very pleased that Jasper's agreed to give this SISAL seminar, since he's worked extensively on trace element incorporation and calcite, but also in aragonite, which is more unusual, but which we know that there are a number of speleothems composed of aragonite, so it's really useful as well. And it will be very valuable to hear what you found and what you have to say, because when we're constructing this version of the database and as we start to use the data, it's just really handy to keep in mind all of the processes and also all the metadata fields that we may need to consider. So thanks a lot, Jasper. And then I pass it to you so we get the full time for the talk and questions.
Okay, all right. Thanks for the intro. Yeah, so when Nikita actually asked me to give this seminar, I first thought like, okay, well, this is going to be difficult to add more information to what Andrea Borsato and Sylvia Frisia already presented. But indeed, like Nikita just said, trace element partitioning in aragonite is also extremely important to get more knowledge about. And especially because the trace element behavior in aragonite and calcite are very different from each other. So one of the most cited processes to explain trace elements in calcite is prior carbonate precipitation. And we have to know which phase of mineralogy is actually precipitating. Yeah, so, okay, so that doesn't work, yeah. So here a short outline for the seminar today. First of all, I will go into more detail about the controls on speleothem mineralogy and its importance for PCP versus PAP. Then I will show how exactly these elements behave differently by showing some results from speleothem calcite aragonite transitions. Then I go into more detail about trace element partitioning in aragonite with a focus on magnesium, strontium, barium, and uranium. And finally, I will show some aragonite trace element records that have been published over the last decade or so, and go and discuss their interpretation. And in the end, I would also like to add some information to how to quantify or identify prior calcite precipitation, and how the variability in strontium of calcite strontium partitioning is affecting this quantification. And then I will finish with some future work outline. So first of all, most of you probably know what prior carbonate precipitation is, but in order to be complete, I would like to give you a very short introduction here. What you see here is a figure from Tremaine et al. 2013, and you see that there are different water flow paths through the cave host rock, and along this water flow path, you can already have precipitation of calcite if the water gets the chance to degas CO2. So what happens when you get precipitation of calcite or aragonite? The amount of magnesium incorporated with respect to calcium is disproportionate. So this means that if you have calcite precipitating before the water reaches the top of the speleothem, then you are basically changing the trace element to calcium ratio in the drip water, especially if this happens at several points along the flow path. And this process is usually related to the amount of rainfall that falls on top of the cave, because that determines the number of air-filled voids in which the water gets the chance to degas CO2. So why are we interested in aragonite speleothems in the first place? Because I mean they are relatively complex in comparison to the calcite counterparts, but they have the huge advantage that they have very high uranium contents. And this means that we can get very good age models with, for example, here, some unpublished data from stalagmite GP5 from Morocco that covers the last 7,000 years and has an average age uncertainty of only 23 years. And another example here, also from Morocco, also unpublished data, a stalagmite that covers almost the last 700 years with an average age uncertainty of just 2.4 years. So that would basically allow to really study decadal timescale changes in climate. So just for you to know what does it look like. Calcite basically looks like this. You have these, yeah, how do you call them? Well, it doesn't really matter how you call them, but they look very differently. I mean, calcite and aragonite, both if you look at precipitation experiments from laboratories such like Alcatip and Eisenhower, #1 in 2017, or their second study from GCA in 2017. You see the aragonite has a much more relatively thin crystals with basically in a fan-like structure. So it's growing in several directions at the same time, whereas calcite has this typical crystal shape, and which looks like, well, sometimes it looks like a columnar calcite fabric in thin sections, which you see on the right side. Whereas the aragonite also has like these aragonite needles in thin sections. It can look like this, where you have these kind of radial fan structures that also show very nice, which also shows very nicely under the crossed nickels or under a polarization microscope. So the reason why they have these different structures is that aragonite has a different crystal structure, which is called orthorhombic, whereas calcite has a trigonal crystal structure. And this means that within the crystal, or within the aragonite crystal, the calcium atom is close to 9 oxygen atoms, whereas in the calcite crystal structure, the calcium atom is close to 6 oxygen isotopes. And this means that there is more space available in the aragonite for the calcium or for the cation as compared to calcite. When this is something that you can clearly see in this figure here, where you have the aragonite crystal structure and the calcite crystal structure. What the consequence for this is that the aragonite tends to incorporate cations that have a relatively large ionic radius, just like, for example, strontium or barium, which are much larger than magnesium. This is why calcite tends to incorporate more magnesium. So, as I explained, you can have both prior calcite precipitation and prior aragonite precipitation in the aquifer above the cave. And therefore, it is important to know what controls the speleothem mineralogy. Now, some very pioneering study from Sylvia Frisia et al. In 2002 already showed that magnesium-calcium ratios are actually very important when it comes to aragonite precipitation, because if you have high magnesium calcium ratios in the drip water, it is more likely to precipitate aragonite. And in this cave, this is Grotte Clamours, these high magnesium calcium ratios are associated with very slow drip rates. Now, other studies here from Rossi Lozano 2016 and Lichterman 2014 showed that drip rate is not an important factor, because you see here drip rate against magnesium calcium ratio. There's no distinction when it comes to drip rate, and that's the same here. There is calcite here and there's aragonite here. There's no relation. But again, the magnesium calcium ratio comes out very clearly. So in Rigelman, I think the minimum magnesium calcium ratio was 0.5 for aragonite to precipitate, and in Rossi Lozano it is around 1. So, but this is, so how does that actually work? So why does magnesium calcium, why does it happen that aragonite starts to precipitate when you increase the magnesium calcium ratio of the drip water? Well, this is a nice study from Niedermeyer et al. 2013, where they did precipitation experiments. And you see that, you see here the nucleation time of the calcite crystals against magnesium calcium ratio. And then you see that, especially for the experiments conducted at 6 to 10 degrees, that there is an increase in the nucleation time of the calcite crystal when magnesium calcium increases. So this basically means that magnesium ions are prohibiting calcite, or they're slowing down calcite growth. So at some point, when magnesium calcium ratio reaches a certain aragonite starts to be more favorable to precipitate compared to calcite. And this is not the only trace element that can force this, because other elements may also prohibit calcite from precipitating. And there is actually an example of that in the literature from Cadeo et al. I think that was in 2012, that study, but I'm not 100% sure. But there they suggested that the zinc ions were forcing aragonite to precipitate. In this study from Niedermeyer et al., they also studied organic molecules as a prohibitor, and that also very clearly shows that an increase in organic molecules, or in this case polyaspartic acid, also increases the chance or decreases the increases the nucleation time for calcite crystals, and therefore may force aragonite to precipitate. Another effects that have been discussed as well in the literature are pH and saturation index for calcite. Rigelman et al. Already suggested that, already showed that there is some kind of relation between magnesium calcium ratio and pH, but it is hard to understand why there would be such a relation, or at least for me, I'm not entirely sure why that is the case. But what she also suggested is that the saturation index for the calcite of drip water is an important factor. Now, what you see here in the Rossi Lozano data is that pH does not seem to have a very large effect. I mean, above 8.4, okay, perhaps you start to get more higher chance for aragonite, but there is a lot of other calcite precipitation going on when you increase pH further. So what I did was I replotted the data from Rossi Lozano and plotted the saturation index for calcite against the pH values. And then what you can see very clearly and very nicely is that aragonite, which are the blue symbols, tends to precipitate when the saturation index for calcite is relatively low. And what you can also see very clearly is that around 8.4, 8.45, the saturation index for calcite that is necessary to still precipitate calcite drastically increases. And now I'm also not entirely sure why this pH value is so important, but there is some indication maybe that it is the carbonate ion content that starts to increase and become more dominant at a pH of 8.4 with respect to the bicarbonate ions. But how this physically works, I am not entirely sure. So the presence of calcite growth inhibitors might actually force the precipitation of aragonite in cave environments. This doesn't necessarily have to be magnesium, but can also be zinc or lead. And on the other hand, there may also be organic molecules that have a similar effect. Secondly, there is the calcite saturation index, which is important, trip water pH. Also, CO2 degassing rates are important. So if you have very fast CO2 degassing when the drip water enters the cave, then those conditions might favor precipitation of aragonite as well. And temperature itself may also have an effect. So high temperature favors aragonite. So so now we know approximately why, a couple of reasons why aragonite may precipitate, and maybe it's not really a surprise that you can also have change in mineralogy within a single speleothem. And so this is what I studied also in my 2012 paper. We analyzed trace elements from calcite aragonite transitions on a relatively high resolution. And here you can see the results. So very, very clearly, we're going from aragonite light gray to dark gray to calcite. Very clearly, the difference is in strontium, which is much lower in calcite compared to aragonite. The same trend can be observed for barium. The opposite trend for magnesium. Uranium also behaves more similar to strontium and barium. Whereas for phosphorus, I think the trend is much less significant, and the same accounts for yttrium. So when you zoom into the calcite aragonite transition, which you see here, you see that especially magnesium, strontium, and barium really increased a lot just before the transition to aragonite. So in this speleothem, it is very likely that it was the magnesium that forced the precipitation of aragonite. Second study or second speleothem, also with a calcite aragonite transition from the same paper. Same approach, calcite aragonite transition, high resolution trace element transect. And this is what it looks like. Very similar patterns as for the other stalagmite. But this is actually a very interesting case, this record, because when you look at the differences in the correlation patterns between the elements, when you compare the calcite mineralogy with the aragonite mineralogy, you can see that the groupings of the elements have changed completely. So here you see magnesium, barium, strontium being relatively close together in this principal component analysis. When you plot the first principal component against the second one, the second group is formed by lead, phosphorus, yttrium, probably related to some organic material, whereas the magnesium, strontium, barium positive correlations can be explained by prior calcite precipitation. But if you look at the aragonite, barium, strontium, and magnesium are completely disconnected, whereas uranium and strontium, two large ions, are coupled together and actually start to correlate positively with phosphorus and yttrium. So my interpretation for that was back then that we might be looking at a prior aragonite precipitation signal. And so here's some more data on that. So with a comparison of prior calcite versus prior aragonite precipitation. This is cave monitoring data from the same cave. And when you plot calcium versus magnesium calcium, you will not see any difference between PCP and PAP. That is because magnesium, because the prior aragonite precipitation strongly excludes magnesium, whereas calcite precipitation also excludes magnesium. But if you look at strontium, it's a different story. So these are the two fastest, the two drip water samples that correspond to the fastest drip rates, and these are the slowest one. These are the slowest ones, and it seems that prior calcite precipitation might be necessary in order to increase the magnesium calcium ratio first of the drip water, and then you can start to have prior aragonite precipitation. And this is actually shown by the trend line here, of which the slope actually represents the strontium calcium ratio of the precipitating phase during prior carbonate precipitation, and then you can calculate with the drip water, with some drip water samples, strontium calcium ratios, the distribution coefficient, and that corresponds to about 1.08 to 1.2, and that is a very good approximation of strontium partitioning in aragonite. So this was actually quite nice evidence for that prior aragonite precipitation occurred in that cave. Then I will go now continue with focusing more on the processes that control aragonite partitioning coefficients. So first of all, a study from 2016. We see that here we used actually calcium aragonite transitions in order to calculate aragonite partitioning coefficients. Just by assuming that certain values for the calcite partitioning coefficients, and then using the measured aragonite partitioning coefficient, or using the measured aragonite trace element to calcium ratio, the measured trace element to calcium ratio for the calcite, and which is relatively well known from the literature, the partitioning coefficient for the calcite. You can calculate the aragonite partitioning coefficient under the assumption that the trace element to calcium ratio did not undergo very major changes occurring during the transition from calcite to aragonite. And in principle, this is of course a minor flaw in the situation, because you have to have some change in the drip water. But the assumption in this study is that you can have relatively minor changes that trigger the threshold towards aragonite precipitation. And then when we do that for 7 transitions from calcite to aragonite in different stalagmites and different speleothems, then you see that they are actually relatively coherent. So this shows that this assumption is not so wrong. Let's say it like this. And you see that that magnesium partition coefficients are indeed much smaller than 1, whereas strontium is somewhere close to 1 or just above 1. Barium is relatively unclear. There are quite a few samples that plot below 1. Uranium mostly plots clearly above 1. And whether it is plotting above or below 1 determines whether the trace element to calcium ratio in the drip water is being enriched, or whether it is being depleted in the trace elements with respect to calcium. And that determines whether, that of course has a different effect, for example, for uranium versus magnesium, because uranium is much larger than 1, which means that uranium is being taken out from the solution at a faster rate compared to calcium. So that would enhance prior aragonite precipitation would decrease the uranium calcium ratio, whereas prior calcite precipitation would increase the uranium calcium ratio. And this story is the opposite for example, magnesium. So what other factors are important for aragonite magnesium partitioning coefficients? Well, when you look at growth rate and temperature, there is this precipitation experiment from Mauro Matis et al. From 2022. You see that they conducted experiments at different temperatures and at different precipitation rates. And you see that the magnesium partitioning coefficient increases when temperature is lower. But what you can also clearly see is that if the precipitation rate increases, then the magnesium partitioning coefficient also increases. And that relationship has also been confirmed, or actually Rinat Gabitov from 2008 were actually one of the first to show that, where they also did growth rate dependent experiments. And you see here that if precipitation rate increases, magnesium partition coefficient in aragonite also increases. And this orange shading also indicates the approximate growth rates for speleothems. So there is an overlap between these experiments and the speleothem growth rates. Now, I have also checked this with the data from this paper, where we can calculate growth rates based on uranium thorium dating. Of course, there are large uncertainties in these growth rates, but it seems that for this growth rate range, that there is no real relation between magnesium partitioning. But I also have to say that we cannot separate the effects from temperature and from growth rate in this study. So it's not very conclusive. What is important to show here is that within the range of speleothem, growth rates, that the growth rate indeed might have a significant effect on the magnesium content of your speleothem. So I'd like to summarize that for magnesium, that for both calcite and aragonite, so that you can see the difference between the two minerals in terms of processes that affect the magnesium concentration. In general, prior carbonate precipitation has an effect. Temperature for both minerals, limestone versus dolostone host rock, variability, of course, incongruent dissolution of dolomite host rock, but also a different balance or changing balances between host rock and soil source. In particular, you can see here in this plot that, for example, dolomite has, of course, dolomite has relatively high magnesium calcium ratio drip waters, but it also has very low strontium calcium ratios. And that's just a very nice trend that you can see here. But so that is how this limestone versus dolostone host rock affects both of these trace elements. When you look at aragonite specific processes, DMG, when you look at aragonite specific processes, like, okay, for example, of course, the magnesium partitioning coefficient is much smaller compared to calcite. Growth rate is much more important in aragonite. We have prior aragonite precipitation, perhaps also a combination of prior aragonite and calcite precipitation. In speleothems, you can also have calcite. In aragonite speleothems, you can also have calcite co-precipitation. And when that happens, that has a major effect on magnesium concentrations. And also because the magnesium partitioning coefficient is so small, incorporation of magnesium also occurs through particulates. Whereas in calcite, of course, it is partitioning coefficient is much higher. And here, maybe also magnesium dehydration processes might be important because that determines how much magnesium is available to be directly incorporated into the crystal lattice. And of course, prior calcite precipitation. So if we look at strontium partitioning coefficients, we'll also look again at temperature and growth rate. And then you see that strontium partitioning coefficient tends to decrease when temperature increases, but the effect of temperature on the partitioning coefficient of strontium is very small in terms of, with respect to the temperature changes that we can expect in caves. So this is not very, again, not that conclusive, because we cannot distinguish temperature and growth rate from each other in this study. Although it appears maybe that there is some aragonite growth rate effect for low growth rates, for low, slowly growing aragonite speleothems, but I think this needs much more. This needs much more research to actually confirm or deny this suggestion. Also important here is a very early study from Finch et al. 2003, which shows the mapping of aragonite strontium, and it shows, again, just like in calcite, there can be quite a bit of lateral variability in the strontium concentration, because the arrow here points at the growth direction of the speleothem. So factors that are relevant for speleothems for strontium, in general, prior carbonite precipitation, again, and these three factors, similar to for the magnesium. In aragonite speleothems, the strontium partitioning coefficient is likely above 1, whereas in calcite it is far below 1. Temperature might have a minor effect, although it is unlikely to show up because the cave temperatures are relatively constant. Then there is prior aragonite and calcite precipitation, but also again, calcite co-precipitation can have a strong effect on the strontium. Yeah, I think that's it for strontium. When we look at barium, there are some precipitation experiments again. Here, early study from Dietzel et al. 2004 and from Gaetani and Cohen 2006 shows that temperature definitely has an effect on the partitioning coefficient for barium, but it very much depends on which curve you are, because the temperature range in these experiments is of course really large, again compared to what we can expect in cave systems. Here's another precipitation experiment from Mavromatis et al. 2018. You see that barium is also related to precipitation rates, whereas this red dashed line shows the precipitation or the barium partitioning coefficient from the study of calcite aragonite transitions. So factors that are relevant for speleothems for barium. Again, growth rate, prior carbonate precipitation. I think the aragonite barium distribution coefficient is approximately 0.91, but it has a large uncertainty, as you can see here. Temperature is perhaps relevant, and then again prior aragonite, prior calcite precipitation, and here for calcite this is about 0.1, 0.3, and prior calcite precipitation might be important. When we're looking at the uranium distribution coefficients in aragonite, growth rate might have a relatively large effect. You see here two studies, or one study from Gabitov et al. 2008, where they studied single spherulites of aragonite, and you can study growth rate or extension rate for the crystals with this, because the time that it takes to nucleate or the time that it takes to precipitate aragonite in the beginning of the crystal, when it has just nucleated, is relatively fast. But when when the aragonite crystal grows, the precipitation rate decreases because the surface area is larger. And this is very clearly seen here in a cross section of one spherulite. The middle, where it grows fast, uranium calcium ratios are relatively high, and at the edge it's relatively low. So again, you see this, then this pattern shows up with speleothem growth rate, approximate speleothem growth rate range indicated by this shadow, orange shadow. So perhaps growth rate is also important for aragonite uranium partition coefficients. But then there was another study from De Carlo et al. 2015, and this study they say they have been able to separate temperature from pH, from carbonate ion contents, and growth rate, and they show that apparently the carbonate ion content of the drip water is very important. That's something you can see here, because it determines the speciation of uranium in the drip water. So this is important because the way that uranium is being incorporated in aragonite is in its form of uranyl tricarbonate, and this seems to be substituting for the carbonate ion in the crystal lattice in aragonite, according to Reader et al. 2000. So when the carbonate ion contents increase, then the amount of uranyl tricarbonate is becoming more and more dominant with respect to uranyl bicarbonate. Yes. So what you can basically see is that the carbonate ion content is important for the partitioning of uranium in aragonite, only related to the speciation of uranium present in the drip water. So factors that are relevant for speleothems. This uranium speciation is not only important for aragonite. I expect that it has similar importance for calcite, and uranium can also form complexes with organic ligands, or for example with calcium cations. And we of course have quite a lot of calcium available, and this speciation may also be pH dependent, although. So this is something that we really need more research on as well in order to explain uranium variability in speleothems. Then there are the usual suspects again. Aragonite. So in summary, the aragonite specific partitioning coefficient is much higher compared to calcite, and because of that, because it is far above 1, prior aragonite precipitation might also be important in comparison, in addition to calcite. So now I come to discussing a few nice aragonite trace element records. Here, this was one of the first records published from Finch et al. 2003 from Cold Air Cave in South Africa. They show if you can believe these. This wiggle matching between the barium and strontium record and monthly rainfall, then it appears that strontium and barium are relatively low or actually relatively high, because it is plotted inverse when it is relatively dry. So that would maybe be an indication for prior calcite precipitation to be dominant in this signal. Another study from 2016 from Morocco. This is in the supplement of that paper. It shows that when growth rate decreases, so these yellow shadings, we see that the delta 13C increases, oxygen increases, or oxygen isotopes, carbon isotopes, of course. Uranium tends to increase, phosphorus tends to increase, yttrium tends to increase, and strontium tends to increase as well. So that would be, if you interpret growth rates as a function of amount of rainfall, then lower growth rates would correspond to drier conditions. Drier conditions means larger amounts of prior aragonite precipitation, and therefore a decrease in uranium, and a decrease, and associated with that perhaps an organic signal or a soil signal from that can be derived from phosphorus and yttrium, and also a decrease in the strontium as a consequence of prior aragonite precipitation. What is also visible in the speleothem is there is a large secondary, or large secondary variability in strontium. So prior aragonite precipitation is definitely not the only factor that affects strontium in the aragonite speleothem. Now, another very nice study from Rone et al. 2019. This is an aragonite record from Mamluk cave of India, which shows very nice seasonal signals in the oxygen isotope composition. And it also shows, in this case, it also shows magnesium seasonality. And they kind of looked at the seasonality of rainfall and how that affects the magnesium calcium ratio in the aragonite speleothem. So in the north of India, rainfall is extremely high. It's basically the wettest place on earth. And during the summer monsoon, if the summer monsoon is weaker, it might have a consequence for prior calcite precipitation to take place, which would mean that if you follow the dashed line, so that is a weak Indian summer monsoon and a wet winter, it would say that you have an increase in prior calcite precipitation in the second half of the summer season. But you see that because of the wet winters, the magnesium calcium ratio or the prior calcite precipitation taking place during that season is relatively less compared to a dry winter. So this basically determines the seasonal signal in the magnesium calcium ratio that is visible in the aragonite speleothems. And like this, they were able to show that there were some years where you have weak Indian summer monsoon and dry winters, or strong Indian summer monsoon and wet winters. Or for example, weak Indian summer monsoon and wet winters, and strong Indian summer monsoons and dry winters. So this is actually a very nice study that I could recommend. A second one, or another aragonite speleothem record from Jameson et al. 2016 from Yokbalum cave, also a beautiful record, very highly resolved, with very clear seasonal signals in the carbon isotopes. And here they used the uranium calcium ratio as a proxy for prior aragonite precipitation. And then they also see that there are phases where carbon isotopes and uranium calcium ratio are anticorrelated, or when they are positively correlated. And these anticorrelated phases were interpreted as prior aragonite precipitation, but these positively correlated times were interpreted as a prior calcite precipitation. This is the last record that I would like to discuss from Wurtzel et al. 2018. Is that again, very nice age model for aragonite, typical for aragonite speleothems, but you can see that in the Raman spectroscopy pattern, that there are phases where you have more calcite and phases where you have only aragonite, and these calcite phases all match up very nicely with very high magnesium concentrations and relatively low strontium concentrations. So this shows what calcite co-precipitation can do with your trace element signal. So in order to quantify prior calcite precipitation, Sinclair et al. Developed a method in which they show that if you plot the natural logarithmic of strontium calcium versus magnesium calcium, that if prior calcite precipitation is dominant, then it should plot on a linear trend line, which has a slope of around 0.877 or 973, which is determined by solely by the distribution coefficient of strontium and the distribution coefficient of magnesium. But there are a couple of assumptions here which are not always valid. So the strontium distribution coefficient is 0.15 or 0.057, whereas the magnesium partitioning coefficient is 0.031. When importantly is that the distribution coefficients are constant and that the initial magnesium calcium strontium calcium ratio of the drip water are constant as well. But this is actually quite unlikely, because strontium distribution coefficients probably are affected by growth rate, and in particular the faster growing speleothems. This might be an issue, and in addition to that, there is also an effect of the magnesium calcium of the calcite itself. So you can see here from a study from 2020 that there is a positive correlation between calcite magnesium calcium and strontium distribution coefficient in compilation of cave monitoring data. And what that means for applying this type of quantification of prior calcite precipitation is that if you have prior calcite precipitation, you increase your magnesium calcium of the drip water and thus of the calcite, which means that your strontium distribution coefficient is increasing while the speleothem is growing. So this assumption that strontium distribution coefficient is constant is not always the case. And if you then plot, for example, the natural logarithmic of strontium calcium and natural versus magnesium calcium, you see that the slopes are actually changing through time instead of having this pure linear trend line, depending on the magnesium calcium ratios of the drip water. Because these are different scenarios. So this is in a limestone cave with low magnesium calcium ratios. This effect on the distribution coefficient is probably small, but where you have more dolomite in the host rock, this effect becomes larger. And you can see that here as a function when you plot the slope of the trend line versus the mean calcite magnesium calcium ratio, you see that the slope starts to increase. And what this means for the drip water is that the slope is not constant either, it starts to decrease. So to conclude, just some future work that is necessary to conduct. We have to do much more precipitation experiments, specifically designed to target trace element partitioning for both calcite and aragonite as a function of temperature, pH, solution composition, but also growth rates. And what could also be extremely helpful is to do much more cave monitoring precipitation experiments. Yeah, and then I will leave it to potential questions.
Thanks so much, Jasper. I've tried to track down some of this information in the past, and I know how difficult it is and how long it takes. So it's really, really great to have these slides from you, carefully examining all of the controls. This is really cool.
Yeah. Yeah. If it is not clear what references I've used, you can also just send me an email or so.
Sounds good.
That is a very good question. So he is asking about potential transformation of aragonite into calcite as a diagenesis process. I think that very much depends on why the aragonite is being transformed into calcite. So if aragonite is being dissolved by a fluid that is undersaturated, and it has a chance to the fluid has a chance to transport trace elements that are dissolved, then you would expect that the calcite that is precipitating from that fluid has a very different trace element composition. And of course, it will already, I think it will always have, no, it doesn't always have to be that the trace element composition of the calcite is different, because if the dissolving fluid gets the chance to flow away from the transformation site, I expect that calcite would have different trace element composition as compared to the original aragonite. On the other hand, if this is a process that occurs in situ, so the fluid is not able to flow away, maybe it is possible that the calcite is being forced to take up the same elements as the original aragonite. But I do also have to notice that I'm not entirely sure, and I think this would be a very nice question also for Sylvia Frisia, and because she has much more experience with diagenesis. But this is an explanation that I could imagine that could be the case. Yeah. All right. Any other questions?
There's a new question in the chat.
Yeah.
So the question of Vitor is, you mentioned organic molecules influencing precipitation of aragonite. Do you think that would also influence the C14, for example?
No, I think that it depends. It depends on how much organics are being incorporated, but I would expect that the carbon would still be dominated by the calcium carbonate phase, simply because it's much more abundant than organic molecules.
I would maybe have a follow-up question to this. So would you think that organic molecules, that they can also kind of make combined effects to kind of change as well the fractionation of the trace elements?
Sure. I mean, I think that how they build complexes with trace elements might actually be important as well, because if organics are building complexes with trace elements, it means that it probably means that less trace elements are available to be incorporated into the calcium carbonate. So I think it will have definitely an indirect effect on the partitioning. Yeah, and also this incorporation of organic molecules or ligands into calcium carbonate phase, I think that's also something that we have to do much more research on, because this different incorporation behavior clearly affects how far trace elements are being incorporated. Yeah.
Great. So if there are no more questions, so thank you very much, Jasper, for the seminar. And we will upload it to YouTube as usual.
Yeah.
And thank you everybody for listening.
Okay. All right. Then have a nice day.
You too. Goodbye.
All right. Bye-bye.